Well, thanks, Carsten, for the invitation, Jens. Thanks for the opportunity. So I'm also looking forward to talking with you guys, so don't hesitate. So the title is a bit, so it's basically two parts, one which is more researchy, the other one which is more survey. So hopefully everybody will learn something, and some might be, teased in some interesting research opportunities. I'm really happy about the structure of the afternoon and the evening. So usually with my talk, I have to think about how am I going to talk about persistent memory, memory-centric, disaggregated. Now I can focus on SSDs and I/O. So that's what I'm going to talk about. The other aspects are going to be covered. So by the end of the day, I think by the end of the afternoon, you'll have a very good overview of different aspects which are very much interrelated. So the interrelation, I guess, will be on you. So for me, I'll be focusing on SSDs and IOs. So it's work. I have some slides from a tutorial that we had Sigmund with Alberto last year. I'll be presenting some work, joint work with Simon Lund from Samsung, and also some work with a PhD student, Niklas Hedam. Finally, Daphne is a EU project. Christian, Alex are involved in it. I'll use that as Konstantin also. I'll use that as a starting point for everything. It's also, in terms of its dissemination in the context of that project as well. So, I had to add the logo, if I can somehow. Yes. So that's a slide from the tutorial. Why you should care. So I've had over the years. So I've been working on SSDs for more than 10 years. There were a few years where I had to work hard to motivate. Why am I talking about SSDs? I was at CIDR and a very prominent person asked me, why should I care about IOs? Okay, I have memory, everything's in memory, why should I care about IOs? So either you use SSDs in your experiment, and I'm happy to talk with anyone about experimenting with SSDs. I won't say much about it in the talk, but if you're experimenting with SSDs, I'm happy to talk because there's a big chance that you do it wrong. So that's, but with this talk, I'll talk about SSD internals. I'll talk about the external interface of SSDs. So you'll get, hopefully by the end, you'll understand that you have to be very precise about the type of SSD that you work with in an experiment. Not two SSDs are equal. You cannot say that your system works with SSD, experiment with one SSD, and think that you established a statement. Okay, you have to either restrict the scope to one class of SSD or work with different classes of SSDs if you want to be general. Some of you might actually design a generation of database or data-intensive systems which is based on SSDs. So not just main memory databases were 2010s. Now we're in the phase where you're in Munich, so Linstore, Umbra, this generation of system, Daphne is also based on SSDs. So you have to have a deeper understanding of how SSD work and what might be possible in the near future. That's the idea of co-design. So I'll spend some time on that. And some of you might be willing to be convinced that there's a research idea, that there's some research in co-designing SSDs and database systems. So we're in the process, a long process of writing a book based on the tutorial. So that's why, principle of database and system and SSD co-design, that's the book we're writing with Alberto. So there are three parts in the talk. First, I'll talk about the storage landscape. Top-down, bottom-up, with the workloads and the kind of architectures we're talking about. Because I'll talk about HPC because it's relevant in the context of Daphne. We'll hear from Microsoft, so the cloud part will be later. I won't talk much about it because I have no insight. I'll talk about HPC here. Then I'll try and make the case at a pretty high level about co-design. So general principles, and then I'll get a bit deeper in terms of internal interfaces. Again, bottom up, looking at all the type of data movement there's within an SSD, the internal interfaces, and then talking about the external interfaces, PCIe NVMe. So I guess if there's only one thing you remember from the talk, it should be about what NVMe actually is in some detail. I/O interfaces, so some work with Samsung, and then computational storage. All good. So in terms of workloads, so as database people, we're working with tables, relational algebra in terms of IOs. Still, I think it's important to think about the different types of way we access storage. The buffer manager, read and write, more or less synchronous or asynchronous. Transaction log and checkpoints, which are two different things. Aggregate scans, but also loading data. Working with any form of spill, external sort, for example. These are different forms of access to storage. And when I talk about co-design, I talk about basically adapting the SSD to a given workload. And from a database perspective, these are the type of workloads that we're talking about. So we can start from there and then define what kind of IOs, how to characterize the IOs that are being submitted in that space. We can do the same exercise with machine learning. You can store samples or models, so either the artifacts, the 1NX model, or associated metadata. Working with matrices, tensors, linear algebra, and then so a sample store and model store type of abstraction, so of random IOs. For HPC, so numerical computing, you either store data from some equipment, so observation, or data which is generated by some simulation. They call that codes. There's a very interesting discussion to be had about what you actually store, because those guys are actually producing way more data than they can store. So there's an interesting, do you compress? Do you refactor? So there's a lot of work which is very interesting in terms of what you actually store. They're working with multidimensional arrays. They're doing numerical analysis, so they do, partial differential equations, the type of curl operators. And in terms of IOs, it's pretty clear as well. So there are classes of things they do. They write data for diagnostic. Is my code running? 1, 2D analysis, so simple first order analysis of the results of a simulation. More complex 3D and 5D, so different, so higher dimensionality of the data. And then they have some form of checkpointing, either end of day, so to restart, so you have a run, and then so in terms of scheduling, you have to stop and then start again, or a checkpoint for resilience. These are two slightly different things. These are the type of workloads that those guys are working on. So in terms of co-design, either we can take each individual aspect and try and have something specific for it. That's how computational storage or near data processing has been handled in the last many years. People have taken one prototype, one type of workload, and tried to accelerate that. Increasingly, there's a trend towards convergence. So Intel has been very active in promoting the convergence at hardware level. Daphne is looking at the convergence in terms of programming language. In terms of workload, we might also want to be able to co-design, to have an infrastructure that makes it possible to co-design for different workloads, not just for one, but for across workloads. So the idea behind Daphne is basically the convergence, the idea that you do a lot of the same things, whether you're doing high-performance data analytics, machine learning, or numerical HPC. And the idea is that maybe you do some small-scale simulation, so you store some data that you use for, so you do some featurization, reshuffling, you then train a model. The model is going to be used for some larger scale simulation, and which you'll analyze. So that might be the several 2, 3D, and that might be 5D in terms of analysis. And the idea is that it might make sense to have the same type of tools, the same type of language to program a lot of these tasks. So a uniform framework for slightly different things. So that's the side of Daphne. There was an overview paper at CIDR 2022. That's the overall architecture. The idea is that there's a high-level language, so domain-specific language. So libraries that, and bindings with different languages. The domain-specific language, some lowering to MLIR, which is used as an internal representation. Some optimization work, which is quite interesting. And then a vectorized engine that takes care of coarse grain parallelism, kernel specific for one platform or the other, so GPU, FPGA, SIMD on a given CPU, and then everything related to storage, so synchronous asynchronous I/O, buffer memory management. Interesting thing is that computational storage, computational is missing here, is across those things. So in the project, I'm in charge of the computational storage work package. So Intel and DLR and Dresden are involved. Alex, sorry. I'm not sure I mentioned you at the beginning, but anyways. And the idea is that this should be working on a local or a distributed environment, and HPC is one of the targets. Okay, so that's the overall idea. And in this context, so Daphne is going to be able to generate workloads which are across some of the workloads I've been describing in the previous slides. So bottom up, what kind of targets, what kind of platform should a system like Daphne be run on? I have a project together with Oak Ridge, so I actually saw the machine, so I took the liberty to describe it. So what's interesting is that there's a lot of compute nodes. They're AMD based, so 4 GPUs, 1 CPU per node, many nodes per rack, many racks. So it's the first exascale machine. So in terms of compute, they had to go big. What's really interesting from my point of view is that they have a lot of what they call local, not local storage, which is basically NVMe SSDs associated within a node. Okay, and they have a few terabytes per node. Okay, so when you get access to the machine, you get access to you get allocated a few compute nodes. I don't know, 50 or whatever, and you have scratch access to the local NVMe disks. So you don't have to ask an administrator for permission to do anything on local storage. It's your responsibility. And then there's a center-wide parallel file system. It's based on Lustre. Lustre is really old technology, but it's still used. So a lot of storage. And what's interesting is that it abstracts from, so there's metadata, resources dedicated to metadata management. As a user, you don't see that. I mean, you interact with Lustre, but behind the scene, there's a metadata tier, and then there's performance and capacity tiers. The performance tier is powered by NVMe SSDs, the capacity by hard disk drives. But this tiering is not something you control. It's something which is managed by Lustre and tuned by the guys in charge of the infrastructure. And then there's the archival system based on Spectrum Archive, which is based on tape. I think there's a lot of interesting work to be done on there, but that's where I am. Okay, and when I talk, when I talk to the guy who's in charge of the infrastructure, here there's nothing we can do. Anything about co-design or computational storage is never not going to make it here in the lifetime of Frontier or even the next generation. But here, when computational storage, if co-design SSDs are respecting the NVMe standard, then they can be plugged in, even in Frontier, or in any type of system that relies on NVMe SSD. So what I'm going to talk about later on in terms of computational storage, in terms of co-design SSDs even, is not completely, it's not science fiction. It's something that can be deployed in HPC systems. To be honest, when we started the Daphne project, I wasn't completely sure whether computational storage could make it into those type of systems. Now I am. Okay, and the key is NVMe. So as a programmer, the type of abstractions you have are either to program on distributed storage, so the parallel file system, you'll be using a Lustre client. In general, you might have, Deos is in Argonne, you have HDFS, which is a comparable. Ceph in Lumi has so the system in Finland has a Ceph. So you have, even if you use GPFS, that's the virtual file system, which is hiding access to the distributed file system. So that's one type of abstraction. And then you have access to the local drives. And the point here is that there's a lot of complexity there as well. How many of you are working with IOs? How many are writing codes where you have IOs? How many of you are working with files? How many of you are working below files? All right. So yes, so we should. So the point I'm trying to make is that the file system is good if you don't care about performance. On NVMe SSDs, if you care about performance, you don't use the file system, or at least you have to have a very good reason for it, because it's going to be in the way of performance. And there are very good reasons to use very lower level abstractions. So I'll get back to that in a few slides. Are we good? So that's the overall view, the Daphne and the HPC system. Why? So that's the one slide, case for SSD co-design. So Flash and SSD are not a new technology. I'm working with a guy now who's been working in '88 with a Cray YMP, which had already SSDs. Okay, so he's saying, SSDs have done everything many years ago. Anyways, the first commercial systems were in the '90s. I started working with them in 2008. These are the first one we actually could buy, 16 gigs Mtron. This standard is actually very important. It's the JEDEC standard. Any warranty, so whenever you buy an SSD, you get a warranty. And the warranty refers to that standard. And that standard is there to enforce compatibility between hard disk drives and SSD. And in particular, it defines the error rate you get when you access SSD. This is new to me. I mean, I found out about this year. For the people who actually work with SSD, it's been obvious for many years. But this has been a key element in the acceptance of SSDs. And basically, a lot of my research over the years has been against this. Right? And part of, you mentioned Open Channel. Open Channel never became a standard because Intel didn't want it, and Samsung had problems with it because of the warranty, because they couldn't refer to that anymore. And the question was, what kind of warranty can they give if they don't have this? So in 2013, NVMe was introduced by Intel, and that was the first, departure from hard disk drive compatibility. That was the first element where a protocol and host to a device standard was devised especially for the characteristics of solid state drives, and that changed the game. So the idea is that SSDs are no longer a drop-in replacement for hard disk drives. They're a component of the architecture, and we should design with them. And so the case is that our tutorial was called no longer GrandPA's SSDs. So GrandPA is programming with SSDs, trying to work around, so massage the workload you have into whatever the SSD is constraining to do. And it's weird because the performance of SSDs are usually very good, but there are cases where they're very bad. Some are very good for reads, some are very good for writes. It's not a fundamental, there's nothing fundamental about this. It's how Samsung or whoever designed the SSD. And as a system designer, you have to work with that constraint. You have to shape your workload to fit the constraints of your SSD. And many different SSDs have different constraints. Whether you have QLC, whether it's an archival system, or whether you have ZNAND and it's very fast, you will be designing in different ways. It's going to shape your workload in different ways. But as system designers, we've been slave of the Samsung designers. The idea is to break away from that and be able to use mechanisms that make possible from the host and the application to control the SSD, so to have richer command. So the work on Open Channel SSD was part of that, lowering the interface. So streams are another way to use a directive, which is in the standard, to communicate from the host to the device, and the device can use this information to work on data placement, for example. What's really most interesting is the opportunity to control internally what's happening on the SSD. And if you can shape that from the host, how caching works, how scheduling works, how data placement works, then you have a way to not be a slave to the design of the SSD, but shape it. So using your workload together with the SSD to find a good way to work together. So that's the idea, to be able to define devices which are co-designed with a given database system. So the path to co-design is long. We're not there yet. One possibility, which is better than the vanilla way of working with SSD, is to configure the device so that's the workload. That's what how the SSD works. You might be able to configure the device a bit so that it's better suited for your workload. So you basically, you have some knobs, you can tune the knobs to configure your device. With computational storage, you can define a new API, which is well suited for your application. Possibly you can offload part of the application to what looks like a device, but it's basically some computing over a standard SSD. That's where we're at right now, and I'll say a few words about this. It's interesting because from the design of that system, this is way more attractive than that. Say you're designing LinStore or Umbra, you want to be able to say, this is how my SSD should look like. For example, transactional writes should be supported. Why not? If you have transactional writes, then the design of your system is going to be very different than if you have a system where you don't know if your write is going to succeed or not. Right? So this is, I think, very important, but it's only a step because you might be able to tailor the behavior of the device by programming. So that's a part of the co-design, but the overall goal is to be able to tailor and possibly offload part of the application. All right, makes sense? So the programming should not be limited to the internal interface of the device, but possibly some more general aspects. Any questions? In terms of co-design, that's all I have. The rest of the presentation is going to be to give you some more elements for why this makes sense, what this is possible, why now is a good time to do it. I mean, this 5 years ago was just science fiction, right? So now we're here. Another element which is very important is the availability of platforms to actually work experimentally with this type of design. The group of Professor Song at Hanyang University has been working for a long time on a project called OpenSSD, where they've been working on developing actual prototype SSDs as a research project, and it's been open. The fourth generation is called Daisy. I mean, you can buy it from a company called CRZ. You have to get in queue because they're a bit late. You know, that's hardware for you. But it's basically an MP sock, so FPGA with ARM cores, connected to peripherals. So, you know, Gigabit Ethernet, PCIe Gen 3. So that's part of the problem because we would like to work with Gen 5, but we'd have to change things. You have basically, you can plug M.2 to M.2 SSD, or you can have, you can plug flash directly. So you can have from the MP sock, you can have the flash controller in the MP sock. Okay, so you can have direct, so that's how Cosmos Plus works. So that's the third generation of an SSD, but they don't have M.2. With this Daisy Plus platform, you can actually do everything. You can have computational storage based on external SSDs, but you can have full control of flash. So again, it's not science fiction. I have a few of those in the lab. They can be bought, and then you can start working. I mean, there's a learning curve, but the more we are working with this, the better. All right, so I have basically half an hour to go over the more detailed part of my talk. I start with the internals. The external, if you're bored, I can go faster, and then we can talk. I'll be here all week. So that's from the OnFi specification. I'll say a word about OnFi in a slide. Basically, I'm not going to talk about how bits are stored on flash. It's interesting, but I think it's irrelevant for us now. Not completely. But the point I wanted to make is that a flash chip, if you look at an SSD, you open it, you'll see a lot of small flash chips. Okay, a flash chip is going to be a lot of so-called logical units, LUNs. And in a LUN, you have a collection of blocks. Each block is a collection of pages. I mean, by now I don't have to say that. I mean, I think you've heard all that. That's not what I want to say. What I want to say is and to be honest, it's not something I've been focusing on the last many years, but it's very important, is that in each chip, so in each LUN, sorry, what you have, the way it's defined, the way a LUN is defined is some flash and a page register. Okay. So for me, in our research, we take that as a black box. So this is what you put in the page register that's the disk representation of your data. Making sense? But you still have memory here. So if you are programming the controller in the LUN, then this is on disk and this is in memory representation. Making sense? And what it means is that you have many, many different levels at which you can work on the representation of your data. This is the late, the last. That's where it ends from our point of view. And so what I'm going to do in the next few slides is talk about the different steps in the data movement. Yes?
So just to understand correctly, does data have to go through the page, or
Yeah.
does it have to be read or to be passed to those?
So so what is interacting with the chips are called flash controllers. And the flash controller has access to a set of pins. So whether it's the right, so you have basically some IOs here, and there's some control pins. OnFi is the standard that defines how you talk on those pins, right? So how to move data and request services, and the flash controller orchestrates basically the access to this. So I think the next slide is an example. So the C here pin controls which LUN is going to be accessed. Then you have control and address latch, so they have to be on. So these are going to be command and address. The rest is going to be data. The clock, whether it's write or read, and then you have basically the IO. So these are basically 8 pins where you have, and the structure is command, column address, row address, the data, and then end of the command. So we're working with a student from Anyang University, which is designing a flexible flash controller. What's cool is that the standard doesn't say, so here you have to have a page. That's where the flash page comes from, because when you read and write from flash, it's at flash page granularity, not flash page, okay? That's why you have a page register here. But this doesn't say anything about pages. What it means is that you might be able to have small pages. Yeah, there's work there, but it's not against the standard. So it's something we might be able to do. Yes.
So,
yeah. Spiros.
There's also more to writing, like things like error correcting codes, right?
That's in 2 slides.
I got what. This page register then is next, like lower level than, for example, the cache in the
That's we had the flash chip.
Yeah,
I haven't talked about. I'm going bottom up.
Oh, okay.
This is the lowest level.
Right. Okay.
Just to get to you to the point is that on-file is a standard, but whenever you cannot just take one flash chip and replace it with another. Both are going to talk on-file, but the error characterization will be very different. So Ono has he's done all the work on this. So it would have been great to be there's been a lot of work on and there are people whose career it is to just characterize flash, not just the error types, but the irregularities in terms of read disturbs and so the different levels at voltage levels. I mean, there's a lot of complexity which is orthogonal with the spec, but it gives us possibility to do cool stuff as well. Yes.
So you said that the Tokyo order that pages, so often like 460 kilobyte pages, is that the page that's there?
I haven't said anything about the size of those pages.
Are these the pages that are commonly these sizes in SSDs? Or is that like an internal page?
No, so
it's completely different.
No, that's the size of the that's going to be 2.4K. But it depends on if you have SLC, MLC, QLC, you will have different page size. Okay. Depending on the number of bits you have per in the array, flash array, you have different page sizes. But this is that's the granularity of interaction with the flash chip. Now I'm going up. You have different flash chips per the way they connect. The way the flash chips are connected to the SSD controller is through channels, so buses. And so you have different chips per channel and channel. So you want to make sure that the channel is busy. So the way you schedule requests on the channel is not neutral. There's that's Alberto's idea is that the way channels are designed within an SSD is not a law of nature. You could design channels, maybe have of them. Today they're very static. You could have a very dynamic way of organizing the relationship between chips and SSD controller. Maybe so to be able to react well to different types of workloads. So that's the next step. From the flash chip with the channel, and the goal here is to hide loon latency and increase throughput. Error correction is the next step. Flash is not. You have bit errors in flash whenever there's no guarantee, or at least there's a guarantee that whatever you write is not going to be whatever you read. You know that. I think it's. I mean, the rates are just crazy. I think it's the rates are 10⁻³ 10⁻⁴. That's the bit error rate. So you have a lot of bit errors. The JEDEC standard I was talking about at the interface level requires 10⁻⁴, 10⁻⁵, depending on whether it's enterprise or not. By the way, that's the difference between enterprise SSDs and commercial SSD is defined in the JEDEC standard, and it's the error rate which is acceptable. Okay, the error rate is lower for enterprise SSD than for commercial SSD. So the idea is to have error correction codes. So whatever you write from the disk from the database is not going to be written on flash. It's going to be encoded so that it can be decoded and so that bit errors can be detected and corrected. Right? So I know too much about ECC. We're doing some work as well on there. So if you want to be able to support small pages, you want to be very flexible in the way you do ECC. And part of the argument we're trying to make is that if you consider ECC as a black box, then you cannot be flexible in your design within an SSD. You have to be able to either do multi-rate ECC or possibly expose the granularity of ECC to the upper layer so that you can do erasure coding in a smarter way, or you can work across SSDs. So there are a lot of things we can do if ECC is being exposed to the upper layers. There's a lot of complexity as well, so we have to find ways to manage it. Yeah, and the thing is that, so there's some ECC that can be done within the chip. and again, as we were saying, the errors, the characterization of error is very different from one chip to the other. So ECC has to be adapted for a given chip as well. And in a co-design viewpoint is that ECC should not just be adapted to the underlying flash, it should also be adapted to the type of workload that we have. So the architecture, putting everything together, we started with the flash chips, the page register here, we have the channel controller, the ECC engine, all that, those two together. So that's the flash controller, which is doing, so flash controller is actually here, there should be one more. Then the two things I haven't talked about is the firmware, that's the FTL. So I've given talk for 10 years where the only thing I talked about was FTL. That's the one thing I haven't talked about today. It's in there, okay? Data placement, scheduling at a high level. And then the host interface controller, which turns out to be a key component of the system. It's basically that's where the NVMe controller is. So interpreting the commands, and most importantly, the DMA engine. So data movement to the host is being managed by this controller here and the DMA engine that it's using. And again, DMA engine it's not a law of nature that they're a black box that cannot change it. You should be able to change the DMA engine so it fits your needs. Any questions? Does it correspond to your picture of an SSD now? And by the way, that's the way Samsung looks at SSD internals. That's the way Professor Song has organized his team around OpenSSD, basically 4 sub-teams: host controller, firmware, ECC, and flash controller. So when I talked with Samsung at the beginning, we were not understanding each other because I was talking about a portion of this, and they were looking at everything. All good? So that's basically the data movement inside. Now I'm going to try and make a case that, so basically there's a lot of data movement, right? So from a host memory to a data buffer inside the memory of the device. Then there's the physical to logical to physical mapping. Then you have queues per channel, and then the data is going to be moved from this queue to the page register. So so some of you are used to working with main memory database where all the data is in memory. There's so whenever you're working with SSD, there are some steps along the way, and opportunities to actually do some interesting work. And that's one thing. And the other thing is that there are decisions all over, and those decisions are being taken by Samsung engineers right now based on what they think is right. Right? They have no idea. So the point is that, and that impacts basically correctness versus longevity. So you have trade-offs all over. How much you utilize the channel is going to be depending on the workload. If you read a lot, if you write a lot, and then you're going to do some OLAP type of work, you're going to read a lot for a while. So how do you trade off? So if you have no idea about what's going on, it's hard. Data placement, garbage collection possibly, caching policy. So there are a lot of decision points. And the point we're trying to make is that those decision points can be hidden behind some interfaces. We might be able to define different levels of interfaces that are basically the internal SSD interfaces. And then we might be able to co-design and write programs against those interfaces. So defining those is future work. So the workload might help with the utility of different pages. So when you do some caching, instead of having LRU, then you might have something which is a bit more appropriate, and possibly a more active caching layer for prefetching. So there are different things that you can do. My favorite as well is how it fits with the DMA engine. So how you push data. So we'll hear about a disaggregated. So in that context, it might be more clear. But even within PCIe with CXL, you want to be smart in where you push to and how you push. or how data is actually moved. So the placement, that's the typical FTL. So that's what I've been talking about for 10 years. What's really interesting is that if you have no idea about the workload, the way all SSD designers are going to work is that they're going to open a block per LUN on a channel. Then they're going to cache everything and then dump, so write everything on all the channels. That's the easiest way to have full channel utilization. And that allows them to have some RAID. So you use, say you have 10 LUNs on a channel, you use 9 for data and 1 for parity. And then when you write everything at a time. When you read everything at a time, and then you can correct. You have a better error correction. So if you want to get to the JEDEC 10-14, you need to have this super page type of they call it RAIN. Okay, that's what everybody's doing right now. Because if you don't know, that's the only thing that makes sense. But if you have some more information, then you can hopefully have some better way. So whether it's possible to do better than that is an open question. But say you're doing a lot of so the obvious thing, you have a key value, so you know how you're going to do a garbage collection. You can take that into account in the way you actually place the pages, so that you have data with the same hotness or coldness on the same pages. That's the obvious thing. But even if you know that you're going to load, and then you're going to read the data a lot. So there might be ways you can actually place the data in a way that is a bit smarter than just striping everything. Or at least you can take the reading as well as the writing into account, while here it's only the writing which is taken into account. By the way, HPC people are working on this problem of trade-off between read and write, but across disks. We're looking at it within the channels, but we can use a lot of what they've done. Channel utilization. So you have basically low-level scheduling. So part of what Alberto has been working on is, so you have transaction log writes, which are synchronous, and then you have checkpoints, which are asynchronous. You know which is which, then you don't have a transaction log write blocked by a checkpoint write. Okay, you make sure that you do it right. ECC Strength, again, that's so we started to do some work on this. So some applications might tolerate more, so 10-10, for example, or you can do ECC at various granularity, and possibly exposing the unit of ECC, just that is going to allow us to do some interesting work. So this is ongoing work. Are we good? Any questions? Yes.
How much do you think you can improve SSD performance over state-of-the-art if you, let's say, make imaginary perfect decisions for all of your decision points?
That's a very good question. The honest answer is that I don't know, and that is going to take some time for us to be able to find out. Because to find out, we have to be able to run so vanilla, so using the DAISY, for example, to run a vanilla thing, and then to say, okay, if we change ECC, what can we get? We're not there yet, but the goal is to get to a point where we can estimate, how to prioritize the work, and does it make sense? So how much do we get? When do we get to 10x? But yeah, we don't have that. But it's a very good point. Yes.
Conceptually, how different is a lot of these? A lot of the things you mentioned, sure, it's a different level, but it sounds similar to like general just writing data to memory or DRAM in this case. So conceptually, how like you have some granularity, like a cache line, I write this, then I have different memory banks it goes to. Conceptually, how much of that is it? Where there's an overlap? Can you reuse kind of like the logical thought process that's going to write into DRAM, also for SSDs, just at a different like page size, I guess. If you think of DRAM as like
no, we'll see what Onur says. But yes, I believe the answer to your question is yes. There's a lot of similarities, and I believe there's a lot of value in looking at what has been done and how much can it be pushed here, and how much of what is taken for granted so within RAM or between RAM and registers, how much of it can actually be done within an SSD, because you're doing a lot of manipulation already. So this notion of in-memory representation. So usually whatever is coming out of the disk is the on-disk representation. Now we can push a lot of in-memory representation inside, I believe. Yes?
You showed a bunch of possibilities how to explore and what you can do at these different decision points. I'm curious in a bit more detail what that looks like. So you mentioned this OpenSSD projects and DAISY platforms, for example. These are, I guess, not things you would actually put into your HPC cluster for productive use. They are largely or more for research right now. But do you think there will be a point in the future where you can change all these aspects, all these decision points on a real commercial or industrial SSD using some embedded ARM processing programmable logic, or will that be more like a thing you have to push to the vendors to hardwire it?
So we can take it offline. I think I can talk forever on this. The short answer is that when I started talking about open channel SSD, so 2011, only Oracle paid attention because they had control over the full stack. And they said, oh, we can do it because we have full control. For Samsung to pay attention, it's taken some time, but eventually they worked with Alibaba on Alibaba doing the FTL and Samsung providing open channel SSDs. I mean, it's not being discussed much, but that's what happened. It didn't work very well because there were a lot of issues in terms of cross-layer, who's responsible for what, but it happened. So my sense is that those things, so if the vendors see a value in it, they'll run with it. And especially the hyperscalers who can do whatever they want. So now it's not just, so 2011, it was Oracle, now it's all the big ones. The question is how much of it they're already doing. And I don't know.
Yeah.
It's likely they've already finished with it. It's That's it. Yeah. But with open channel, we were, 5 years behind them, but nobody knew. I mean, so a few people knew. But. So I'm going to have a few slides. I go quickly over those slides. I'm happy to talk if you think it's interesting later. PCIe, I thought I knew what it was, but I had no idea. PCIe is a networking protocol. It's a layered protocol. The key about PCIe is that there's a very strict requirement about writes. Whenever you have a write request, so you have requests at the top level, and then they go, different levels. What's really interesting is that, so basically we have read and write request, and the write request has to be serviced within 10 microseconds. Okay, so whenever a host writes to a device, the device has to acknowledge the write within 10 microseconds. Okay, what it means is that if you write to an SSD and you wait to go to to flash and all that, it's likely on most systems that you don't have time to write everything down. Making sense? So there's a need for something around PCIe to be able to deal with writes to disk. That's one point. The second point is that the DMA engine is on the SSD. So I don't know how much you know about DMAs. I don't want to go into more details. I'm happy to talk about that. If you're working with data movement, this is absolutely central, I believe. There's been a series of paper on basically writing DMAs for so RDMA and all that. So I think there's a lot of work which is very interesting in the context of SSDs as well. So my point is that it's not very complex, but you work with SSDs, you need to understand this. So back to the write constraint. The reason you have NVMe is to deal with this constraint. And basically what NVMe is queue pairs, queue management. NVMe is nothing but queue management. I mean, it's a lot of things, but at the core, when, this afternoon when we'll hear about, I guess, CXL, you have memory coherency. What's the role of NVMe? NVMe is going to deal with queues, basically. And completion, submissions and then completion. Am I making sense? Those queues are located in memory mapped address space, either on the host or on the device. And they are basically two memory management model. Either the queues are on the host, so there's a host memory buffer, I mean, regardless, there's a host memory buffer and then the controller memory buffer. HMB, nobody talks about it, but CMB, you might hear about it. So it's basically memory on the device. And it's memory mapped on the host. So you have a portion of address space on the host, you write an address in that, you're going to go read or write memory on the device. Am I making sense? And then there's PMR, which is basically persistent memory backed CMB. So they designed something special, especially for persistent memory. It's persistent memory on a device, which is made available to the host. So just a plug for in terms of transport models, it's been designed for PCIe. So that's basically the shared memory between the host and the device. But there's NVMe over fabrics, either with a message model, so that's on top of fiber channel or TCP, or a mix of message and memory. So you can have shared memory over RDMA. Okay. So most of my work is in that space, but there's also the disaggregated aspect, which is actually very interesting. In terms of abstractions, you have the concept of a namespace. So with NVMe, you have a portion. So I think in the standard, it's a portion of a non-volatile memory. That is a namespace. And to a namespace is associated a command set, or possibly several command sets. A namespace, so basically, in the standard, you have the notion of NVM sets, endurance group, and domain associated with a given controller. Okay, so an NVMe controller is going to work with possibly different namespaces. The notion of NVM set makes it possible to have a low granularity. You can represent loons in the NVMe standard. So if you might have a controller that supports the fact that you expose each loon as one namespace. That makes it possible to work with the geometry at host level. So you're getting closer to open channel. Endurance groups are basically namespace backed by the same type of flash. So you can have SLC or QLC. These are going to be different endurance groups. And then a domain. In terms of command set, you have the administration, you have the fabrics. The most interesting for me are the IO command sets. You have the NVM command set, which corresponds to the block device, read and write with basically flat logical address space, quantized in blocks. So LBA 0, 1, 2, 3. And then you can read and write. Okay, that's the traditional abstraction. What's interesting is that there are two additional command sets in the standard. Key value, which is interesting because so it's basically you have keys of a given size and then values which are arbitrary size. So you can have the key value command set is a way to send small data to a disk, right? You don't have to be quantized at block level. Key value has been defined for a while. Nobody cared because there was no driver in the kernel. And now with some innovation I'm going to talk about, it's coming back. And people are actually starting to work with key value SSD. And then there's ZNS, zone namespace, which is a standard derived from Open Channel. So the Matthias and Javier, who worked on Open Channel, defined this standard. And it's basically, instead of a logical block address, you have zones. Each zone, in each zone you write sequentially, and you have to erase the zone before you can write again. And you can have different a number of zones open at the same time. So again, command set are associated with a namespace. So I think I said a few words about this. The directives, I talked about streams. That's basically a way for applications to work with the SSD, to communicate. So streams are the only directive in the standard, but you can think about ways to use them to have a communication directly from end to end. Another aspect which is not discussed here is the end-to-end data protection. So there's a way to communicate metadata together with the data from end to end. All right, so I think I have 2 minutes. So I'll I'll say a word about I/O interfaces and then I stop. So all computational storage, you want to hear about computational storage, come and see me. I/O interfaces, the way I think those of you who work with files, that's how you work. You basically have a storage for you is read and write, and you have an API. All right, that's how things have worked for a long time, and it's worked very well. So that's basically the POSIX API. You have a file system, you have a lot of layers, and that's fine. Okay. Today, this is from a talk by Simon at C-Store this year. So there's a link to the YouTube video. Today, you have a lot more complexity. You have different types of device where you can, so basically you have zone reset. So you have different, it's not just the NVM set with NVMe device, you have key values or zone commands. You can have some more information. And so you have synchronous read and write, but you have asynchronous ways to work with that. So you have different libraries. You have POSIX IO, lib.io in Linux. Windows is something different. Then you have IOU ring, which is the modern way of submitting IOs. Then you have ioctls. Recently in Linux 5.19, so the Samsung group in Copenhagen just pushed a new way to submit IOs. So basically talking directly through IO ring to the NVMe driver with asynchronous ioctls. So ioctls are usually synchronous. So in efficiency, now it's possible to have from applications, from user space, you can talk directly to an NVMe driver using asynchronous ioctls. What it means if you is that SPDK is so you don't need SPDK. You can use that to bypass the entire kernel and talk from user space to an NVMe driver using a Linux mechanism. Right? So that's a very big improvement. The problem is that you have a lot of complexity. Which one do you use? How does it impact your system? Do you design for lib.io or do you design for IOU ring? So for example, your SPDK, you had your NVMe driver, and you were very happy about that. Now, asynchronous ioctls are coming in the kernel. How do you actually take advantage of that? And what Intel has done is they went to Samsung, and so the system Simon developed is called xNVMe. It's basically a thin layer, which is basically a narrow waist between different types of application, different types of command sets, and all the IO interfaces that you can dream of. So now you can write your application against an xNVMe. Is going to work on different types of IO interfaces. And this is now how SPDK works. So the block device in SPDK actually is on top of xNVMe, which is on top of SPDK. Okay, the block device is on top of xNVMe, which now allows it to be available on all IO interface. I believe it's the only way to work as a data system designer. You work with IOs, you have to work with xNVMe. Again, I'm happy to talk about that later. I think I'm done. If I go to the takeaway on navigating the design space, so we're about here with computational storage. Again, I'm happy to talk with that. There's a lot more work on getting to the co-design, and part of the question you were asking are what is going to lead the way. And NVMe is a central part of this. The only way it might succeed is because of NVMe, because it's there, because it's extensible, and because it makes it possible to innovate on top or below. And the idea is to be able to find what the mechanisms that are being used for computational storage. Instead of working on top of SSDs, we can work on top of the internal interfaces to actually get to SSD co-design. Thank you so much.